Hi, today I'll presenting our work on multi-modal pipeline defect localization, a collaborative effort by Mariam, Manzoor, Zahra, Arabi, Narei, Henry Leung from University of Calgary, and Scott Miller from Baker Hughes. And this work has been accepted to the third Muslims in ML workshop co-located with NeurIPS' 2024. About the motivation, pipelines are essential for transporting oil and gas, and ensuring their safety and reliability is crucial. There are two common non-destructive evaluation techniques, which include laser profilometry and magnetic flux leakage, as we call it, MFL. For laser profilometry, it provides high resolution, precise defect shapes, and on the other hand, magnetic flux leakage detects pipeline anomalies by analyzing disruptions in magnetic fields, which making it ideal for larger scale inspections. Integrating these two methodologies helps us to get the higher accuracy profile defects in larger scale inspections. But it will introduce challenges like data misalignment, label noise, and domain shifts between laser and MFO. And this motivated us to explore the performance of state-of-art model to address these challenges. Our contribution include analyzing the challenges of integrating MFO and laser data, evaluating how label noise and domain shift affect state-of-art models, and providing insights into the limitations of current approaches.
We started off with labeling our dataset. Our dataset consists of 33,000 samples, where each sample contains a laser image and triaxial MFL signals. And the MFL signal include a signal in axial direction, a signal in radial direction, and a signal in circumferential direction. To define defects, we use laser data as ground truth, and we generate defect masks and bounding boxes using ortho thresholding. We also apply data augmentation techniques such as translation, zoom, and horizontal flip to improve our model's generalization. On this slide, you can see an example of the original laser image, the MFL axial signal, radial signal, circumferential signal, and the combined three-channel input, along with the defect mask and bounding boxes we detected from ortho thresholding. Our primary framework for defect detection and segmentation is mask RCNN with a ResNet-18 backbone. The MFL data is the input for our model, and the bounding boxes and masks derived from the laser data serve as our ground truth. The primary objective is to detect the defect profiles as close as possible to the original defect of the pipeline, which is represented by the laser image. In our evaluations, mask RCNN outperformed YOLO, particularly at higher confidence thresholds, which is also visible in the table shown in the slide. Interestingly, using ResNet-18 with FPN did not significantly improve the F1 score compared to using a standard ResNet-18 backbone. An interesting observation in that table is that the recall rate across all confidence threshold is low, which highlights the persistent challenge in reliably detecting all defects close to ground truth. One key issue, which is also visible from the sample shown in the slide, is that the defect with lower confidence score often are filtered out as false positives during evaluation. Our model is not confident in differentiating noise, which looks like a defect, from the actual defect. Moreover, the mismatch between ground truth region and input feature patterns reveal complexities beyond alignment or box size discrepancies. For example, in this sample, the false positives actually sometimes represent the defect, but they don't exactly match the ground truth by the laser. They are smaller boxes within a larger box and have very low IOU, which is our metrics for comparing the ground truth with the predicted boxes.
For the segmentation part, first we try to evaluate the outputs of mask RCNN. As we saw the discrepancies in the outputs, we try to analyze other segmentation models that doesn't based on region proposal approach. We tried unit and different variations of units, like adding attention gates and using the transformer-based encoder for the unit. You can see the scores of dice, Jacquard, and accuracy for all models here in the table. Although scene units are outperforms mass Gaussian in Dice and Jacquard scores, but you can see the results remain unsatisfactory, and we see all consistent discrepancy in all models that I'm going to explain in the next slide. Here in the figure, you can see that the first row we have the 3-channel MFL image, and the second row is the laser one, and the mask which is extracted based on auto thresholding is overlaid on the laser one. And the predictions of two models, swing unit R and the mask Gaussian, are obvious in the figure. As you see, we have some discrepancies that come from a domain gap between laser and MFL signals. And the defect characteristics in MFL doesn't have point-to-point mapping with the laser-based ground truth mask. And also, we have inaccurate ground truth annotations from laser images. And as you see here, it fails to precisely define defect regions and boundaries for samples, which introduce label noise, and it somehow hinder model from capturing meaningful patterns and overfit on the nodes. For the conclusion part, we analyze the performance of different models on defect detection and segmentation, explore the effect of label noise and domain shift, and also we show that because of this misalignment between MFL and laser, the state-of-art models can perform well. For future work, we will focus on modifying loss functions, exploring domain adaptation techniques, and noise-robust architectures to improve defect detection and segmentation performance. Thank you.